Okay, let's go ahead and get started. Um, good morning or good afternoon, good evening, depending on where you are. I'm Robert Crowe, and I'm going to be talking about production ML for mission critical applications. So ML ops tends to be complex. There's a lot of moving parts, but what I really want to do at the beginning of this is to step back and think about really the big picture. What are we trying to do here? And fundamentally, what we're trying to do is we're trying to model a part of the world. We're trying to model a process, a series of events, a body of knowledge, some area that we want to use in a product or a service or a business process. So it's that's what we're trying to do. And if we're so what we do is we go out into the world and we gather data, and the data that we can gather are things that we can measure. Although there is also unstructured data that we can gather that has predictive value and information in it. What I'm going to focus on here mainly is supervised systems, where typically we're working with things that we can measure. And it's really very much like what we do as humans when we're trying to study something, a new skill or a new area of knowledge that we're trying to learn. So it's very much the same kind of a thing. We go out, we look for information, we try to understand things. And as data scientists, we often start by taking a data set that we've gathered or been given, and we start working with the data, trying to understand it, and start doing our first modeling of it. And we're often doing that in a notebook, like what we're looking at here. Um, and that's how that journey starts. If we're in research, we work through working with the data and the model to develop a result. And then we write up our results as a paper and publish it. And then we're kind of done at that point. If we're working in ML ops in a production ML situation, especially for mission critical applications, that's really just the start of our journey. We have our very first model, our very first data set. Great. That's a good start, but it is just the beginning. So throughout this conference, we're talking a lot about ML ops. Again, I want to step back a little bit and think about fundamentally, why do we need ML ops? What are the big things? Because again, there's so many moving parts in ML ops, it's easy to get lost in the detail. And I'd argue that there are two big reasons, and really only two big reasons, that we need ML ops. And the first is change, and the second is process. So we're going to talk about that. We'll start with change. And to do that, we're going to do a little thought experiment where we're a retailer. So this is a business situation. And the thing that we're selling are shoes. And we're trying to figure out where we can get data to help us decide how much inventory to order. And click-through rates are, one source of data that tell us about customers and what they're interested in and what they might be buying. So that's working fine at the beginning, and then suddenly our model starts doing poorly, maybe measured as AUC, on a particular part of our inventory, men's dress shoes. So as a retailer, that's a problem. And the question is why? Why did our model go from performing well to performing badly? It's important to understand why. And more than that, it's important to know how would we know that we have a problem? How can we be alerted? Because if we're just running the model in production, we have no signal to tell us that our model is doing well or doing not so well. Unfortunately, if we're really not monitoring and looking at the ground truth that our models should be reflecting, then we end up with situations where you have a business process that fails. You're either ordering too many shoes, in this case, for our example, or not enough shoes. That's not a situation that you want to get into, and that's one of the fundamental motivations for MLOps is avoiding situations like that. So going back to the question of why did our model start suddenly doing not so well? There's multiple possible reasons for that, but a core one is change. Something in the world changed. Our model was not aware of that change. So it's still predicting based on what it knows about the old world, the previous state of the world. There could be a new competitor that entered, styles may have changed, something, whatever it was, changed and was not captured in a new update of the model. So that's one motivation. The other big motivation is process. We're working in production, in a production process, and we're using machine learning, but it's important that we understand that we need a production level process. We typically focus on the model, which is, very important, of course, for any machine learning. But in production, we find that, at Google, we've measured the modeling code to be something like 5% of the total code necessary to put a model in production and operate it successfully. So all the other pieces that you see here, these are all parts of an MLOps infrastructure solution, and it includes the ML model itself, but all the other things here are critical to success. And unfortunately, people discover this the hard way, often. Hopefully not as much as they used to. But this is a fairly famous tweet from 2018 when MLOps was still fairly new. And it's a typical situation, unfortunately, where they have a model in 3 weeks, and then there's, 11 months later, still trying to deploy it. So Google has exactly that same problem, or had exactly that same problem. I think we're fairly mature at this point. And we did a lot of research. We continue to do a lot of research into it to look for ways to improve it. And we publish a lot of papers that are out there that are available for you to read and learn more about different aspects of operating machine learning in a production environment. So for production machine learning, we're doing machine learning. So we have all of the same challenges that any machine learning development has, assuming we're doing supervised learning, which is still predominantly what people do. We need labeled data. That data should cover the same feature space as the prediction requests that we get. And it should cover it fairly well so that we don't have regions that are overly sparse. We want to minimize the dimensionality in order to really optimize our system. And at the same time, we want to maximize the predictive data, either through feature engineering or just through feature selection. We do need to be concerned about things like fairness, which are very important and increasingly important in the field. There's also rare conditions, depending on the domain that we're working in. Autonomous vehicles, for example, rare conditions can be extremely important. So we need to make sure our training data covers those. Or we have other systems that will deal with it when our model fails. And a lot of this really gets down to data and model lifecycle management. So we're going to manage both our data set as it changes over time and our model as it changes over time for the lifetime of our product or service or business process. So that by itself is a lot. But in production, we're also working in a production environment, and we have a piece of software that we're going to put into production and operate it. So we have all of the same issues that we have for any software deployment, any production software deployment. We need to be concerned about scalability. We need to make sure that we've written the system and the infrastructure to be extensible. We should have strong configuration management, and our results should be consistent and reproducible. We want to make sure that we've, created things that are modular and we can work with them flexibly. We want to make sure we follow best practices, or at least if we haven't followed best practices, we've done it in a thoughtful way. We want to make sure that our system is testable, which is a little different in machine learning because we have pieces like data sets that are often not part of a typical DevOps solution and the unit testing that's done for that. Monitoring is incredibly important, both in any software deployment, but especially for a machine learning deployment. And safety and security, you don't want to overlook those. There are attacks that happen against models with various outcomes. They can, pull information about your training data from the model. They can pull a lot of the information of the model architecture itself. They can attack the model just as a denial of service kind of a thing. So you want to make sure that you've put systems and processes in place to deal with that as well. So what is MLOps and why do we need it? Well, again, we get back to process and change. But let's look at a definition. So this is one definition. There's several out there, but they all kind of coalesce around, the same sorts of ideas. So this says it reasonably well, I think, that MLOps is an engineering culture and practice that is really trying to unify ML system development and DevOps, so it's ML with ops. And it means that you're looking to try to automate and monitor things as much as possible, including things like testing and releasing and so forth. So along with that, there are several key parts of that process. So just like from DevOps, we have continuous integration and continuous deployment. We also have for MLOps continuous training. So for continuous integration, we need to test not just our code, but also our data sets and make sure that they conform to the data schemas and our models as well. Continuous deployment is, again, a little different from DevOps. So we no longer have just a single software package or service that we're dealing with, but we have this connected system of a ML model and the inference infrastructure used to serve it. And we're deploying one into another and managing versions and so forth. And continuous training, of course, is unique to MLOps, where we're trying to make sure that our model accurately reflects the current reality that it's dealing with. And that gets back to the change that we talked about earlier and how the world changes, and our model needs to change just like humans do to adapt to change in the world. So most people start with a fairly manual process when they're just starting to implement MLOps. And you got to start somewhere. So especially for a small team with only a few deployments, this is a reasonable place to start. You're doing things fairly manually, but at least you're getting it done, and you're thinking about all the different issues that you need to deal with, and you're doing things like collecting your model in a registry and so forth. So it's a reasonable place to start. As you move forward, as you mature as a team and an organization, and you start deploying more and more into production with different models, you need to develop a more automated system. And so this shows really the kind of system that you'll end up with. There's a development environment that you're going to work in to do the development and updates, experimentation for your models and your data sets. And there's a production environment that you're going to really deploy things into. And you'll notice, for example, that your feature store crosses between both of those. So there's some commonality here. And one of the key parts of this that is common to both are the pipelines. So in the case of development and experimentation, you really should be doing that in a pipeline. You might do some of your experimentation before you move into a pipeline, but since you're going to be deploying this into a pipeline in your production environment, it's important for you to do that development and testing before you do that deployment in a pipeline style. And of course, once you get to your actual production environment, that's when you're really working in a pipeline. The pipeline is really important for automating the processes that you're going to go through, so that even when no one is there monitoring it or watching it, it's still operating. So at Google, we've had, again, exactly these same problems, and we have a ton of models all over the company that are in production. And so we developed TFX, which is actually the third generation of ML ops infrastructure at Google. And it's what we use currently for our, well, not all of our production ML, but the vast majority of it. So it's used in a variety of products that you're probably, I'm using Chrome right now. You may use Gmail, for example, or YouTube. It's used all over Google. And it's used in Google Cloud products as well. So Vertex AI and Dataflow and BigQuery, it's used all over the place. And this is kind of a high-level look at the production components that make up TFX, and in some sense, is sort of a general model for MLOps pipelines in general, but it is specific to TFX. So at the top, in gray here, these arrows are the tasks that you're going to need to go through really in any pipeline. We do that through some libraries that are open source that really focus on different parts of that set of tasks. And then those are leveraged by components that form the pipeline. So these are the TFX components that, actually these are the components that just come out of the box when you do a pip install, but you're going to end up adding your own custom components to this pipeline as well. So this is what I call the hello world of TFX. It's a different look at it. It shows some of the data dependencies. So on the left there, you can see we're ingesting data. These orange components are our training pipeline. So they're ingesting data, and then we do some analysis of the data set, the statistics for it. We generate a schema of the different features. So looking at both the types of the features and things like ranges of numerical features or the valid categories for categorical features. We do some comparison of that to make sure that the data, at least at a high level, looks correct and alerts for anything that like a value that is beyond what the range should be and so forth. We do our feature engineering in a component called TensorFlow Transform. Actually the component is called Transform. The library that it uses is called TensorFlow Transform, and you can use that separately. And then we train our model. The model can be a number of different formats. It doesn't have to be TensorFlow. We do some deep evaluation of our model performance. And we also deploy our model into a bit of a shadow environment just to make sure that we can actually run it before we hand it off for pushing into a production environment. So the production environment could be a number of different styles of deployment. You could be deploying into a serving, a server or a cluster using something like TensorFlow Serving, but you could also be deploying on a mobile device or into a web browser, or you could just be saving it off into a repository like TensorFlow Hub, and maybe using that later for things like generating embeddings. In green, we have an inference pipeline. So if you're doing batch inference or bulk inference, you can also use TFX, and one of the things that it's going to do is distribute that inference over a cluster for you. This is all backed by a metadata store that's going to keep all the artifacts that are generated through your pipeline, which are important. We'll talk about that in a second. So first, let's take a look at what is a TFX component. There's really three parts of it. This is at an architectural level. There's three parts of it. Really, when you're working with your own component, you often don't really see this level of detail, but let's talk about it. So the driver is giving your component the input that it needs. The publisher is taking the results of the component and putting them back into metadata. Oh, let me go back. The executor is really where the work of the component is done, so that's what differentiates different components, really. That is where you do most of your work, really probably all of your work most of the time. If you're creating a custom component, it's going to be in the executor. So the way this works is it's really leveraging the metadata store, except for the very first component that's reading from some data source. All the other components are reading their input from the metadata store as metadata artifacts. Then the component is doing whatever it does based on a configuration and in some cases user code. And then it creates its result and pushes that result back into metadata. So what that does, well, first of all, it does that over an abstraction called channels. So there are input channels and output channels. And there's some annotations that go along with it that make that very flexible to work with. But what that does is it gives us this data-dependent flow through a pipeline. So you have an upstream component that does its thing, produces an output, pushes it into metadata. Components that depend on that result, that they have a data dependency, then start up, they pull that artifact from metadata, they do their thing, and so forth. And that's how data flows through the pipeline. It's based on data dependencies. And the things that flow through are artifacts. They could be data sets, but they could also be things like statistics or metrics for your data, schemas, or other kinds of artifacts that you might be interested in. So one of the key aspects of TFX is portability, because it's very powerful to be able to work both in different styles of development and different development environments, and then deploying into different production environments. So one of the things that we've tried to do is really make TFX run just about anywhere. And it kind of does. You can run an entire TFX pipeline in a web browser by using Colab, which is a Jupyter Notebook environment that's hosted for free in a web browser, or other similar kinds of environments. You can do it all on your laptop. You can run the whole thing on your laptop. You can also work in a containerized environment using Kubernetes. Or you can work in a managed environment using Vertex AI. For orchestration, again, you have a choice of different orchestrators. If you're just running in a Jupyter Notebook and stepping through cells, really that's Python orchestration. You could also use Apache Airflow to do orchestration, or Kubeflow pipelines to do orchestration. And for processing, the compute resources that you're going to need to run this thing, it could be your notebook, or actually, if you're running in a Colab environment, it's a VM hosted somewhere. You could be doing that processing in a Spark pipeline. or a Flink cluster, or you could be running on Cloud Dataflow. So you have a lot of choices for all of these pieces, and you can kind of mix and match among them. Orchestration in a notebook is a great way to do development, and it's a good way to really get your model working and do not just exploration, but you can do debugging and so forth. To do that, you have what's called the interactive context that keeps track of the artifacts that are produced. Well, it's the context really, because your artifacts are going to be tracked in ML metadata. But as you step through, you're running in the interactive context. The metadata store, I mentioned a couple of times, is really a key component here. So let's take a look at it. So what's in the metadata? Well, first, everything that's in the metadata is artifacts. Each of those has an artifact type and a definition, and they have properties. So things like trained models are artifacts, data sets are artifacts, schemas are artifacts, statistics are artifacts, and so forth. One of the things that is kept in the properties of artifacts is the context. What execution are they associated with? Because you want to be able to reconstruct the journey through a pipeline to understand how the pipeline generated its results. So that becomes important to understand the provenance of data across your executions, which, especially for regulatory situations or legal requirements, or just to study and understand the results that you generated, data provenance, or it's also referred to as data lineage, can be very important to understanding that. We do a lot of the processing, the actual processing of things in a distributed pipeline cluster, because we want to be able to work with large amounts of data. We want to be able to work with petabytes if we need to, and we often do. So to do that, we use Apache Beam. Apache Beam is an abstraction layer that sits on top of other distributed processing frameworks. It also includes, however, the direct runner, which implements its own processing. So you can run Apache Beam by itself without having a Flink or Spark or Dataflow cluster behind it. But that means that you're going to be running on the system where you're running. You're not distributing that out to other compute nodes. It supports a number of SDKs in different languages. The one that's used in TFX primarily is Python, although in a containerized environment, you could use any of these. So the way that Apache Beam works is there's these different compute clusters that it can work on. And there's these different SDKs that you can work with Apache Beam. And Apache Beam sits in the middle of that. It takes its operations and data in its SDK. It translates that into the native SDKs for these different clusters, and it generates a result. So looking at that a little differently, we have a TFX component that is running somewhere, either in a full OS or a Docker container, and it has an executor that wants to get some processing done. So it's going to work with Beam. It's going to create a Beam pipeline using one of the Beam SDKs. Beam is going to translate that and send it off somewhere to a distributed processing cluster that's running something. Could be Spark or Flink or Dataflow or whatever. It's going to generate a result that's going to be translated back into the idioms of the Beam SDK and delivered back to the executor of that component. So for example, when we do feature engineering with Transform, that's how we do it. We send that off to a cluster and get the result back. There are standard components that come with TFX when you just do a pip install, but that's just where you start. you add to that with your own custom components. So again, this is the kind of the hello world look, and those components that you're looking at in orange and green are the standard components. So starting with the beginning of the pipeline where we're ingesting data, we have example gen. And example gen really is just a configuration. So there's a number of different formats that you can work with that come with just example gen by itself. You can also add custom formats, and you can also support formats using Beam. So by leveraging the formats that are read through by Beam, so Kafka, for example, you can ingest data into your pipeline with your example gen. It's going to split your data based on your split configuration, but by default it's training and eval. And again, it's going to use Beam to do that processing. One of the things it does is split large data sets into spans. So each span will have splits, and you'll have a number of spans based on the size of your data set and the size of the spans. The next component is statistics gen, which really tries to understand the statistics of your data. So this is giving you, as a data scientist or machine learning engineer, a look at your data to help you understand it and make sure that everything makes sense with the current data set that you have. Again, it's using Beam to do this. And it has this visualization that you can use to really kind of dive into your data and understand it and really kind of take it apart, at least at a high level. Then we have schema gen. Schema gen is going to infer a schema for your data. So that includes not just the data type, but things like for categorical data, what are the valid category values, and things like what are the ranges for numerical values and so forth. Example validator takes both those statistics in that schema and it looks for problems. Often in development, what you'll do is develop a schema early in the lifetime of a particular version of your data set. And then rather than run schema gen again, you'll save that off and just import that schema. And in subsequent runs of your pipeline, you'll generate new statistics for the new version of your data set and compare that with the previous version of your schema to make sure that you haven't had anomalies or bad data that has creeped into your data set. Transform is where we do feature engineering, and transform is really the first component where you're writing code. In order to use transform, you need to create user code that defines the feature engineering that you want to do. So that's part of what you give to the transform component. Before this, it's all been configuration driven. It takes the data from example gen and the schema and also your code. It's going to produce two different things. First of all, it's going to transform your data, but it's also going to create a transform graph, which mirrors the transformation that was done on your data. In fact, it's used to do the transformation of your data. And that's done using Beam. Trainer is where you train your model. So it's taking the results of your feature engineering along with your schema. And here's another place where you're going to need to supply code because you need a model. And trainer's going to use that and train your model. Your model could be TensorFlow using either Keras or Estimator. I'd encourage you to use Keras. Estimator is one of the older styles and at some point will be deprecated. But really, any Python-based modeling framework will work in just a standard trainer component. If you need to work in a non-Python modeling framework, you can do that by using a custom container component, which is one of the ways to create a custom component by containerizing a component. There are advantages to using TensorFlow, and you know that's one of the things to consider when you're choosing a modeling framework. But you are not limited to using TensorFlow. We have examples of using other frameworks like scikit-learn or JAX. So just to emphasize that again, people are training XGBoost, especially for the TFX add-ons community, or PyTorch, or JAX, or scikit-learn, or TensorFlow. I don't know. There may be DL4J or things like that. I'm not really aware of people using that, but it's certainly possible to do that. One of the things that you get with TensorFlow is you can use, or actually for PyTorch as well, is you can use TensorBoard. So TensorBoard is a great way to understand your training process and the metrics that were generated by your data, by your model rather. And one of the nice things about TensorBoard in a TFX environment is you can pull previous model results from previous training runs. Could have been, something you did 6 months ago, and compare it to the one that you're doing now in TensorBoard. So you get this visual comparison of the model training process that can be really useful for understanding how things changed over time. Next, we use Evaluator to evaluate the results of our model. And we do that at a deep level, not just at the top level of, like the AUC or the RMSE for our entire model over our entire data set, but looking at individual slices of our data. So you remember earlier we talked about men's dress shoes in that example that we looked at. That would be a slice that we'd want to use to evaluate our model performance, to make sure that our model does well, not just at a high level, but across individual parts of maybe our inventory or our business or days of the week or something. Because if our model performs badly on any of those, then that impacts that whole set of use cases. And there's a set of customers, or there could be a set of customers or business processes that are going to see that those bad results and be impacted by them. And this is another place where we give you some visualization tools to help you really understand things. So in this case, we're looking at the start hour for taxi trips. And you can see that we do much better in some times of day than others. So we want to be aware of that and maybe gather some more data for those different times of day. We also want to make sure that we've considered model sensitivity, because if we're working with prediction requests that are outside of where we've trained our model, we can have model sensitivity that drives our model to really large amounts of variance, and that can be especially in critical situations like autonomous vehicles, it can be extremely bad. So we want to make sure that we've considered that and tried to study both our prediction requests and our training data so that we've accounted for these situations, and maybe put in business processes in the event that we see requests that are outside of where our model is really able to do reliable prediction. So one of the ways to do that is to explore a model and look at counterfactual examples using tools like the what if tool. So it really helps us understand the sensitivity of our model by playing with the data and our model and really diving in and looking at an extremely granular level how our model is doing on a variety of different metrics, to understand how it does and really how sensitive it is to things like counterfactual examples. It gives you a lot of different visualizations to help you understand your model. It's you can spend a lot of time really analyzing and understanding your model at a very granular level with the what if tool. And there's other similar tools available as well. We then have the infravalidator component, which performs a really simple but very important task. It deploys your model and tries to run some requests with it to just make sure that the thing will run, which is fairly basic, but you definitely want to know if your model's not going to run for some reason. So there's a number of reasons that it might not, if the signature is bad, for example. So this is a key component. And then if all of those things pass, and especially if your model is actually doing better than the one that you've currently got in production, which is one of the things that evaluator does. It compares the one you just trained with the one that you have in production currently. If the one that you just trained is better, then you want to deploy it. You want to use it. And pusher is how you do that. You push it into a deployment target. It could be a file system target, or something like TensorFlow serving or Cloud AI pipelines, or what have you. So I mentioned earlier that the green components in that Hello TFX slide are a batch inference pipeline. Bulk infer is the component that is used to do that. So you're going to give it your unlabeled examples and a trained model. It's going to use Beam to run inference across a compute cluster and produce a batch of results. So if you're able to run batch inference, which in a lot of cases you are, things like recommender systems or what have you, this is a great component to have. I mentioned a couple of times that you can develop your own custom components. So let's take a quick look at how you do that. There's three main types of custom components. The easiest one by far to work with is just a Python function that you create by adding a decorator and some annotations to a Python function. We'll look at that in a second. You can also create a component using containers where you can do whatever you want to do in that container. The only requirement there is that you maintain the contract between the input to the container and the output that is produced by the container. And you can take a more Pythonic approach by extending the existing component classes, either for components that you've written or the standard components that come with TFX. When you build your own component, it's just a component. It just plugs into your pipeline just like any other component. So looking at a Python function-based component, you can see that there's this decorator here in orange that I'm adding to a Python function, and then some annotations for the arguments to the function. So those are my input artifacts and my output artifacts. I can also add a variety of parameters or custom config to the component. And I'm going to produce output, including as a dictionary, but also I'm going to push artifacts into the metadata store using this output artifact here. And then the component code is whatever, and it returns your output dict. For a container-based component, if you're familiar with Docker files and you're used to working in containerized environments, this will look very familiar. You're going to wrap your container in this function here running in Python. It's going to have a name, and then the inputs take these annotations and parameters and so forth, their outputs. You're going to have an image that you're going to start from, and then you're going to add your layers on top. And then this command that starts up and runs your component. So very similar to a Docker file. That's how you create a container-based component. So how can you implement MLOps? Well, you need a number of different components. I'm using component too much. You need a number of different things. One of those is a training pipeline, and that's what TFX is. The metadata store is also a part of TFX. But these other things, like the serving environment, monitoring, the experimentation environment, these are outside of TFX, and you need to think about what components you're going to, or what pieces you're going to use for those parts of your infrastructure. So again, TFX forms the training pipeline and includes the metadata store where you're going to have your artifacts and models and so forth. For serving, you might use TensorFlow serving, or you might use something like Vertex AI prediction or NVIDIA Triton or what have you. You could also be serving on a mobile app or in a web browser. So you need to think about those deployment scenarios as well. For experimentation, you could be doing a number of different things. You could be working in a web browser. And we looked at some of the portability that the TFX gives you. So you really have a number of different choices for different experimentation environments. For feature stores, there's Vertex AI feature store, but there's also the Feast feature store. And the TFX add-ons community team has just released an example gen that ingests data from Feast. So what are others doing? Let's take a quick look at what some of other people have done to implement their MLOps solutions. Waze is one example. Waze is the world's largest community-based traffic and navigation app. Some of you probably use Waze. I do. They had a number of different challenges. They have a lot of modeling to do, and they have a large amount of data. And it's geospatial data. Along with that, their team really needed something that was easy for data scientists who are not necessarily machine learning engineers to use. They wanted to use a managed solution, and it needed to be customizable and scalable. And they wanted to make sure that it was Pythonic as well. So what they did is they started with TFX, and then they added a layer on top of it called TFX data, or Waze data TFX rather. And what that did was it created this deployment workflow for them that was very easy for their data scientists to work with. So what they do is they fork a repo, they make some changes in the config and the code, and then when they deploy, the rest of the process is automatic. So when you commit a configuration file to the code base, it gets deployed, it sets up continuous training, and it sets up the pipeline, including all of the TFX and Vertex AI stuff. And things flow through unless issues are caught, and then things are stopped. So it's a very, very powerful way for their team to work. Digitech Galaxis is another example. This is a retailer. It's actually the largest online retailer in Switzerland. And they were doing a reinforcement learning situation where they wanted to do some deep personalization using 12 different recommenders for their newsletters that they send out to their customers. Latency, even though they're running in a batch scenario, they did have some latency requirements that they needed to meet, and they wanted good engineering practice. They want to make sure it was modular and generalizable and so forth. So they created a contextual bandit model that selects between the different recommenders based on reward calculation in a reinforcement learning scenario to do the customization for individual users of their newsletter content. This is a kind of an architectural diagram of their solution, looking at the different cloud components that they use. There's a lot here. If you want to take a look at this at a deeper level, there's a blog post up on our blog that dives into the details of this. This is looking at it at more of a sort of a TFX-centric view of things, where we're ingesting data, we're running through statistics and transforming training and so forth. So again, this is all covered in the blog post. Looking at the inference environment, again, we're ingesting from BigQuery. We're pulling a model, and we're using bulk infer because we are running in a batch environment. And then storing our predictions in a data store on the cloud. OpenX is another example who's implemented an MLOps solution. They're the world's largest independent ad exchange. They have an amazing amount of data. They have more than 1 million requests for ads every second. So for inference, they have very tight latency requirements and an incredibly petabytes of data that they have to work with very frequent model updates. So this is a very demanding environment. They went through a transformation because they were previously running this in their own data center and they wanted to migrate onto the cloud and they wanted to do it. This is sort of building the airplane in flight. They were making this transition as they're operating the business. The results, though, were really remarkable, and they were really happy with how things turned out. So by leveraging TFX and the approach of TFX along with the MLOps style of architecture that we try to encourage, they were able to really deliver some great results. So at the end of the day, this is what their TFX pipeline looks like. You can see they've really tried to simplify it because of the amount of processing and data that they need to work with. So it's really kind of bare bones, but this is what they work with in their production environment, and then they're monitoring and running testing in a development environment as well. Spotify is another example. So Spotify, in this case, they're transitioning not just onto the cloud, but they're transitioning from a Scala-based solution into a Python-based solution because they could kind of see that Python was really where the community was going. They were a very early adopter of TFX and Kubeflow pipelines, and one of the things they did is produce their own fork of things and work in it, which they're now merging back. But you can see, I mean, they've said 7 times more experiments in their environment. So they've been really happy with the results. So how can you learn more about MLOps and TFX? Well, a number of ways. There's a website, of course, with tutorials and user guide and API reference. We have a 4-course series with Andrew Ng that goes through not just TFX, but machine learning engineering for production in general and MLOps. So we cover a broad range of topics. And we have a community group that I encourage you to join if you're working with TFX, if you're developing components, or you want to develop components or tools or libraries. We meet every other week. There's the link to join, and you can look at our repo. So happy to have you. And here's some links as well. I'll go ahead and leave that up, and then we should probably go to Q&A here. So there's a number of questions in the chat. Let me start at the beginning. Elise is asking, did anyone catch that link to the levels that he referenced earlier? And Mateus answers, I believe that is the correct link, Mateus. That is taken from some work that colleagues of mine did, Khalid and Yarek. So that really goes into a lot more depth of what the different levels are. Are the slides publicly available too? Kinda. I can't, there's a bunch of artwork in the slides that I can't, because of the licensing on it, I can't release that. So the slides are really kind of not available publicly, I'm afraid. It's stock art that we have a license to use, and I can't give that out for other people to use. If we need to use GPU for different, so Alriza is asking if we need to use GPU for different steps, component of the pipeline How can we manage GPU to avoid out of memory issues? CUDA out of memory. Yeah. Um, well, that's a problem with GPUs. They have a limited amount of memory, and if you're going to be working with them, you can easily exceed the memory that they have. Your options are use a GPU with more memory, or try to reduce what you're doing on it to fit into memory. It's one of the challenges of doing ML engineering on a GPU. I don't really have any magic answers there, I'm afraid. Maybe somebody else does. Athera is asking, is the model artifact stored outside metadata store? If so, how is it connected to the rest of metadata artifacts for reproducibility? Okay. So the artifacts themselves are stored in a database, and that database is the metadata store. So, but it's a database, so it's something like MySQL or uh, what have you. But the payloads in those artifacts, if they have a payload, not all artifacts do, but things like a data set has a payload. It's a large amount of data. You don't want to store that in a database typically. So that is stored outside in some sort of block storage, maybe a file system. And then there's a URI in the database that points to wherever that payload is stored. So that's how those are kept in sync. Nicholas asks, very nice presentation. Thanks. Well, thanks, Nicholas. In the context of Vertex AI, what are the advantages of using TFX compared to Kubeflow pipelines? Are they both supported? So yes, Nicholas, they're both supported. The advantages of using TFX are that TFX is really designed really for ML. So if you're doing ML, TFX has advantages in that, and the fact that it's really Pythonic. If you're working in Kubeflow pipelines, it's more of a Kubeflow style of approach, which is more configuration driven using protobufs and so forth. It's also more flexible in terms of being able to use it for things other than ML, so for data engineering, for example, or other kinds of pipeline flows. At the end of the day, I think, in my view, what it gets down to is what style of environment are you more comfortable in working in? If you're more of a Kubernetes developer, then probably Kubeflow is going to be more familiar and easy for you to work in. If you're more Pythonic and maybe an ML engineer, then TFX is going to be more familiar and easier to work in. In general, you can do the same things in both. There may be cases where one does something that the other doesn't do. I'm really not aware of any, but there could be. Chris asks, in the batch inference, how is this done? Does it use a deployed model or package the model inference code to use to apply on dataset column? Okay, so for batch inference, it uses the trained model, and it runs on the pipeline using a beam operator called run inference. So what that does is it distributes the inference across the cluster and feeds each inference request across the cluster, and then gathers the results into a batch. So it's using the deployed model, and it's using the beam run inference operator. And how is this compared to MLflow? So MLflow, I don't really know a lot about MLflow. My impression is that it's more focused towards Spark style of development. and probably in Spark pipelines. But again, I really don't know that much about MLflow. Christian asks, would you have some tips in terms of accessing the metadata store? For example, are you building custom dashboards? Also, how could we enforce standards around metadata management using the store? Uh, so for accessing the metadata store, it's important to understand the data model for metadata, which is available. It's in the documentation. So understanding things like context and so forth. There's also some tooling that you can use for performing queries. One of the things that I didn't talk about was TFX nodes, which do queries like importing from the metadata store or doing resolution of artifacts. So you would use those to pull metadata to do custom artifacts. Artifacts are often represented as protobufs, and enforcing the standards are based on the protobuf definition. Standards could cover a lot of ground, but if you're talking about the format of an artifact, that's how that would be done. Okay, I think I'm out of time. In fact, I think I went over a little bit. Sorry for that. But appreciate all the questions, and there's those links. You can go out and get some more information. So thanks very much, and enjoy the rest of the conference.